Hi, I'm Arshad. I'm going to be presenting our work on dynamics-aware unsupervised discovery of skills, or DADS as a shorthand. I'm presenting this on behalf of my collaborators from Google and UC Berkeley, Shane Gu, Sergey Levin, Vikash Kumar, and Carol Hosman. Looking at the recent trend in machine learning, having a large amount of data seems to be mandatory for both better performance and better generalization. This is exemplified by the ImageNet dataset, which spurred the onset of deep learning models for computer vision. More recently, language modeling and understanding has undergone a similar transition through BERT and the subsequent models. These approaches have been reliant on pre-training on a large amount of language data. What does this mean for reinforcement learning, particularly deep reinforcement learning? We want to provide our agents with more interactions and more data, which can potentially lead to robust, generalizable, and complex behaviors. Unfortunately, this has not really panned out thus far, with reinforcement learning being restricted to relatively small datasets and curated behaviors. Why is this the case? The conventional approach in reinforcement learning is to design a task, then specify a reward function, and then use some off-the-shelf algorithm to maximize the expected reward. However, designing the right set of tasks is quite cumbersome and even untenable at large scales. Even if we are given a task or a desired behavior, specifying a reward function can still be extremely non-trivial. To see that, we show a few problems with the reward-based learning paradigm. Firstly, reward engineering can be quite tedious. These massively engineered rewards need to be constructed to get the desired behaviors, such as the one shown in example here. Moreover, there are several problems of interest where it is unclear how to specify the reward functions. There are several interesting research directions which bypass some problems of reward specification, such as inverse reinforcement learning or imitation learning. Nonetheless, these approaches require this per task effort, which can still be cumbersome. For example, generating a set of demonstrations for every task. A promising approach to generate such new behaviors at scale is the field of unsupervised or reward-free learning. Prior work has shown non-trivial behaviors can be learned without any explicit rewards, both in continuous and discrete control environments. The exciting prospect about unsupervised learning is that it can bypass the problems of reward and task specification while still being able to generate complex behaviors. Before we jump into our work, here is a very brief primer on the current methods. The key idea in prior work has been to discover a diverse set of states by using mutual information to construct task-agnostic reward functions. To see how that pans out, assume each skill is parameterized at pi a given s comma z, where the skills are sampled from a fixed prior distribution p of z. One way to maximize the diversity of skills is to maximize the mutual information between the states and the skills. This works because mutual information quantifies how much two random variables can predict each other. To see that, let's look at the decomposition of mutual information in terms of entropy. Here, mutual information quantifies a reduction in the entropy of the skill Z when the value of the environment state S is revealed. This effectively means higher the reduction in entropy, the more certainty with which we can identify the skill given the state, which just consequently implies that skills are reaching a diverse set of states. The idea of using mutual information to reach diverse state spaces has been used in several prior works, which have been listed here. However, in context of skill learning, we want to identify if there's more to skills than just reaching diverse set of states, and can we formulate other constraints for better skill discovery? In particular, we want to motivate the idea that skills should be predictable. For the given instances, what is the difference between the behaviors on the left and the right? On the left, the events seem to be out of control of the actor, while on the right, the agent exhibits a great control over the environment. We have this notion of predictability associated with the skills, that is, when a skill is executed, the consequences in the environment are controllable and hence predictable. This notion of predictability transfers to the more familiar robotic setups as well. In the Mijoko agent behavior on the left, it does not seem to be a skill because the consequences of the agent are not predictable, while on the right, the agent seems to have the systematic gate with predictable transitions. So the question then becomes, how do we incorporate this notion of predictability into our skill learning objective? To that end, consider the mutual information between the next state S prime and the skill Z, given the current state S. At a high level, the goal of our policy would be to maximize this quantity such that the next state can be known from the current skill and the state. In this work, we will focus on this particular decomposition of the mutual information. Notice, this decomposition implies two things. First, we want our marginal entropy of transitions to be high. That is, we want different skills to lead to different transitions. And secondly, we want the conditional entropy to be low. That is, we want transitions to be as predictable as possible when we are given the value of the skill. This satisfies our desiderata of the learned skills being both diverse and predictable. The take-home message from this slide is that the notion of predictability in skills can arise if we optimize the right mutual information objective for our skills. Unfortunately, the quantity by itself is intractable to compute and optimize. We provide a high-level explanation on how to do so, but a more thorough and detailed derivation is in the paper. By definition of mutual information, we get the following equation. Here, the expectation is taken with respect to samples from the stationary state distribution, which in practice just amounts to generating a batch of episodes from the current policy. Now, unfortunately, both the quantities in the numerator and denominator are intractable. We can use a variational lower bound to replace the intractable distribution in the numerator with a variational distribution Q S prime given S comma Z, where the parameters phi denote the parameters of the neural net. For the intractable denominator, P S prime given S, we resort to approximations. In particular, we use the marginal of a variational distribution over the prior P of Z to approximate P S prime given S. By taking the Monte Carlo estimate of this approximation, we get the reward function for DADS, which is described in this last equation. Before we move on to the actual algorithm, notice something peculiar about our variational distribution Q S prime given S comma Z. Our variational distribution allows us to predict the next state given the current state and the skill. This can allow us to simulate a trajectory of the skill in the environment without actually executing the skill. The exciting bit about this observation is that it provides us an alternate way to do model-based reinforcement learning, that too with hierarchical abstraction. We discuss our variational approximation a bit more. Firstly, we call our variational distribution Q as skill dynamics. While conventionally models such as PS prime given S comma here have to approximate the dynamics of agents for arbitrary behavior, skill dynamics Q will only model the dynamics for one behavior Z, which is generated by our underlying skills. Estimating skill dynamics can be easier than the global model. To see that, let's revisit the example from earlier. While the global model will have to model the dynamics for all behaviors, such as the one on the left, skill dynamics may only have to model relatively simpler behaviors, such as the one on the right. This is especially the case for our setups, where we are rewarding our skills to be predictable and thus easy to predict dynamics for. With this understanding of skill dynamics, which we will revisit later, let's describe our skill learning algorithm DADS. First, we initialize our policy and the skill dynamics. Then, in every iteration, we sample a few skills from our chosen prior distribution, and we roll out the episodes from the sampled skills to gather the transition data. Next, we train the skill dynamics on this batch of data, and using the skill dynamics, we label all the transition in the batch with our DADS reward. With the rewards labeled, we can use any off-the-shelf RL algorithm to learn our policy and critic from this data, and we repeat this till convergence or for a fixed number of iterations. The algorithm is generic and thus in principle can be applied to any domain. For our results, we want to answer three questions. First, we want to look at what kind of skills are learned by DADS. Second, we want to answer the question whether the skills learned by DADS are actually more predictable. And third, we want to see if we can leverage the learned skills on downstream tasks. Particularly, we want to test model-based control using skill dynamics. To answer the first question, we visualize the skills learned by DADS in various Mijoko environments. For the ant environment, we see that the ant learns a diverse set of skills for locomotion, with different gaits and direction providing a good coverage of a large portion of Cartesian space. We also see that the diverse gaits are generally smooth and predictable. DADS can also scale to the Mijoko humanoid environment, which is a very high-dimensional continuous control problem. Again, it discovers a diverse set of locomotion skills with smooth and predictable gaits. In some of our follow-up work, we explore the application of DADS to non-locomotion domains, in particular manipulation domains. We find that the algorithm is able to control the valve to provide continuous rotation in different directions, as shown in the behaviors here. We move on to the second question now, where we want to test whether DADS learns more predictable skills. For this, we compare the skills learned by DADS on the Mijoko ant environment to those learned by Diane, or diversity is all you need. Diane is an unsupervised skill discovery algorithm which is suitable for continuous control environments. Note, Diane only optimizes the skills to be diverse and not necessarily predictable. We visualize the trajectories generated by the skills learned by ant using DADS. Here, the same color represents the same skill was executed. Compare this to the trajectories generated by skills learned via Diane, which shows significantly more variance. It's clear that that does improve predictability of our skills. Now we move on to the last question, where we want to see if we can leverage our learned skills to solve downstream tasks. We will use model-based control over our skills, but a couple of points first. We will be planning at a skill level, not at an action level. The actions will be generated by our learned policy pi of a given s comma z. Second, we want to emphasize that the skills and the skill dynamics are already learned. At test time, we only provide a reward function, which can be estimated as well. This enables very sample efficient solution tasks, even zero shot if the reward function is known at the test time. We provide a high level overview of the planning algorithm. First, we generate a sequence of skills, which we plan to execute in the environment. We simulate the trajectory for each of these sequences in the environment using the learned skill dynamics and policy. Then we compute or estimate the rewards for our simulated trajectories, and we use all this information to update our planner, which will give a better plan for skills in the next iteration. We do these iterations for a fixed number of iterations or till conversions. To see the model predictive control in action, we test our learned skills for ANT on goal navigation for sequence of goals given online. Note, this video was generated zero shot, where the agent only observes the reward for the current goal. The combination of MPC using skill dynamics and skills learned using DADS is able to navigate for a sequence of goals. Similarly, we can do this for Humanoid too. The Humanoid is a significantly more complex control problem, and thus, the skills learned are a bit more restrictive in terms of what goals it can achieve. However, we find that it can still do reasonably in the same testing setup. Quantitatively, we want to benchmark our performance of model predictive control, or MPC, using skill dynamics. Our baseline is the conventional model-based RL, where we learn the global dynamics model PS prime given S comma A, and then at test time we use MPC to solve the task. We choose the task of goal navigation in the ANT environment. For this plot, lower scores are better. We start with the conventional model-based RL variants. For the first variant, we learn the dynamics model using only random exploration without any rewards. At test time, we test this model on randomly sampled goals. For the next variant, we learn the dynamics model with goal-directed exploration, where the goals are sampled randomly from the fixed distribution. We test on the same distribution of goals. For the last variant, we learn the dynamics model with goal-directed exploration for a single goal only, and at test time we use the same goal. Next, we have the DADS and the MPC with skill dynamics. For the first variant, we learn a discrete set of 20 skills, and for the next variant, we learn a continuous space of skills which is sampled from a uniform distribution of -1 to 1. As you can see, both of our variants outperform all variants of model-based RL, despite the second and third variant of model-based RL benefiting from seeing the test time task. We also show that using DADS is feasible in the real world. In some of our follow-up work, we improved the sample efficiency of our algorithm to do skill discovery on real-world quadruped. We also demonstrate that the goal navigation can be done in real life using these learned skills and their dynamics models. To conclude, we provide some key takeaways. First, optimizing skills to have predictable consequences in the environment can result in much better discovery of skills. DADS can provide a meaningful way to leverage already learned skills using model-based control. This provides a competitive alternative to conventional approaches for reward-based learning as well. We also provide a mechanism for planning with hierarchical abstraction, with skills being executed by the low-level primitives. We believe that our work provides an opportunity for new work to be built upon. One interesting direction is the following. The skills which emerge from DADS depend on the state space in which we do skill discovery. Can we study the effect of state space representation on the skills? And can we learn the state space representation to discover skills which will be useful on the downstream tasks? Thank you for listening.